Okay. So we're going to have, it's almost like we're going to split class into two classes today. It's going to seem like two different topics, but these topics are really both sides of the same ideas. Part of what the first part is going to be about is establishing some basis for what we're doing in set theory and probability in ideas of logic. And if we have time, I might draw some logic diagrams. I'm not sure that we'll have that kind of time. This first part, I'm going to be sort of like flying through these, to be clear. And I'm not expecting y'all to ingest all of this, retain it, but I want to show you kind of a set of laws from which we can build kind of incredible complexity. Boolean logic or set algebra, like circuit design, is based wholly on these things. And the set of laws that we have here can allow you to do circuit construction and circuit simplification and things like that. You might see this sort of thing in electrical engineering. Is definitely part of computer organization as a discipline. For us, we're going to think about it a little bit in terms of sets, more of it in terms of the Boolean operations that we perform on a regular basis. And you're not likely going to write such complex, or anytime soon, such complex Boolean operations that you'll need these laws to simplify those things. But it is good practice to know these, right? And what you're going to see when you're in the DSI is that when you build large Boolean masks, is what we call them, when you have a data set and you're trying to develop the truthiness and falsiness of what's happening across that data set, a lot of these kind of reductive logic approaches are going to apply, and not in all cases. And you can definitely find simpler procedural ways to do things, but having a basis in kind of formal logic, or in if we just want to think about it as Boolean logic, having that basis is going to be helpful in constructing control flow, in program design, and in other spaces. So this looks like a big list of laws. That's essentially what it is. I'm going to do some pen and paper stuff as we go. And part of what I was doing earlier today, and why we started a little bit late, is I was writing out code justifications for most of these. It used to be that I would live code the proof, well, not proof, but the Python, exemplification for all of these. But I think that's actually really boring to watch, and you're going to have all the references down here, as you can see. So for any of these laws, we've got the set logic and the Boolean logic in Python, but I think it's a little more interesting to show it in pen and paper. So that's what I'm going to do. The main laws that you're going to want, the main law that you're going to want to understand coming out of this, it's the two laws, De Morgan's laws. And we're not going to test you on that in the technical interview for the DSI, but it's very common to be tested in technical interviews for jobs on De Morgan's laws. There's a kind of assumption that you know De Morgan's laws, and that you can do some simple simplification. You can do some rudimentary simplification of logical statements. So hopefully this slide deck, set it aside as a resource, put it in your notes somewhere, and just have it as a reference as you go forward. Okay, so I kind of hand waved this a little bit before in the last lecture. We're going to think about set union as being analogous to the OR operation in Boolean algebra. Intersection is going to be analogous to AND. Complement is going to be analogous to NOT. And we're going to see that pretty quickly here. So set operations, the set operation union and the set operation intersection are commutative, and we can think about this in terms of code, right? Like, if we take the union of two sets, then what we get out of it is going to be a new set composed of the elements, the unique elements across set 1 and set 2, right? Across the sets that we are performing the union on. Now, does it matter if we do set 1 union set 2 or set 2 union set 1? It really doesn't. It really doesn't. And if we think about that in terms of a Boolean operation, and I have the code for that here, but let's just look at it this way. If I say, and I'm just going to use T for true and F for false. If I say true or true, that is going to be the same as, well, let's do it like this. If I do true or false, that is going to be the same, right, as false or true. Those are equivalent statements, right? So we can reorder them at our convenience. And similarly, how we group a union or an intersection is or let's say 3 unions or 3 intersections. That doesn't affect the outcome either, right? And that's kind of what we're seeing here. So this applies to sets. If we take the union of set 1, set 2, and set 3, that's the same as taking the union of set 2 and set 3 and then set 1, right? And the same applies to intersection, right? Because when we're thinking about intersections, we're just thinking about membership. We're thinking about, well, what element is a member? What elements are members of all 3 of these? So when we're representing these in terms of grouping, it's equivalent to think of the intersections of A and B, then the result of that intersected with C. That's equivalent to intersecting B and C, and then intersecting that against A. All of that is equivalent to an ungrouped form of this. Just A intersect B intersect C in any order, right? How we think about this is purely associative. Now, don't take this too far and think something like this is associative, where we have A, B, union C. This is not going to be necessarily the same as A, union C, intersect B. It's not commutative across those operations. It's only commutative for either intersection or union. Okay. So this is where we can start thinking about a little bit about reduction. And let's say that we have well, let's use one of these. Let's use this one in particular. And I'm going to do some set reduction as we go. I don't want to focus on it too much, but I do think it's interesting. It's kind of fun. There's a little bit of puzzle solving when it comes to this as well. So, okay. So if we're thinking... Oh, sorry. I'll put this over here. If we're thinking A or B or C, we can reduce this. We can say, so A is true, right? B is false, so true or false. Those are grouped. And then C is true, so or true. So if we reduce this, true or false, that reduces to true. True or true, that reduces to true, right? So we can do the other side of that operation, A or B or C, right? So that's just, we can say true or false or true. and we can reduce false or true to true. Then we've got true or true, which reduces to true. We can see that those are equivalent, right? True is true. Okay. So those two are the simple ones, the easy ones. Let's get into some that look a little more complex. We've got this distributive property, and I think this is pretty interesting. This mirrors the distributive property in algebra. So if we have the intersection of B and C, we have this intersection upon which we perform a union, right, with A. We can actually distribute through B and C. We can distribute A through B and C, right? So then we get A union B intersected, right? Here's the intersection. A union B is intersected with A union C. So let's just work through this from a Boolean standpoint. Feel free to run any of this code that's in the slides. I think it is nice to see this in a set justification. But that said, it's more the Boolean approach, the reduction here, that I think is kind of cool. So I'm going to use just these values, this true, false, true. And let's just verify this for one of these. Okay. So we're considering, so A is true. And we're going to think of union as or, right? So this is true or, and then B is false. So B is false. And we're saying false and C. And C is true. So false and true evaluates to false, right? And needs truth on both sides. So false and true reduces to false. True or false reduces to true, because for or, we only need one of them to be true. Okay, so let's think about this. Let's think about the other operation. I should have given myself a little more space here. So we're saying true or false, and true or true. Okay, so true or false evaluates to true, and that's going to be ANDed. True or true evaluates to true, and then true and true, we meet both conditions for the AND operation. That evaluates to true, okay? And we can see that true is equivalent to true. Okay. And all right. So that's distributive. And if you carry out that operation, with this other form of distributive, you're going to see that holds as well. The main thing, as I said, I want to just show you these set reductions, these Boolean reductions as we go. And I think some of these are pretty interesting. Okay, so the Idempotent Laws. This is just, showing when we have the idea of redundancy, redundant operations. And I think this is like a tautology, right? This is very straightforward. If we have, A, if A is true, right? Or let's say A is false. So if we have A is false, then if we say false or false, right, that just reduces to false. So we can see that false, we can see that this first version here that would hold, right? And it would hold for AND as well, right? So let's say B is true. We can say true and true, well, that just reduces to true. So that's just a kind of simple tautology, but we refer to it in logic as we refer to that in logic as idempotent. Now we have something that's a little more abstract, and that's the domination law, or the domination laws, I should say. So we've got these special sets, and we've been talking about S as kind of our superset, upon which we have a subset A, or subset B, or subset C, something like that. Now, we can think about S also as U, or the universal set, okay? So if we have the universal set, that is everything. It's every element that we have the potential to utilize in our problem. So if this is, I don't know, 1, 3, 9, 27, and 41. That's everything. That's our whole universe of stuff. Now, if we have a subset, A, and A is, let's just say 3 and 9, then we intersect A with U, right? A intersect U is fairly simple to see. If it's just the intersection, well, it's just going to be these values in common. We wouldn't expect to see anything else in there. So it's just going to be this element and this element. And so the intersection of A with the universal set is just going to be 3 and 9 in this case, which is just going to be A. So we can see that. Similarly, like if we intersect anything with nothing, right? And that's this other special set, the null set. This is what the null set looks like always. It's just nothing in it. You don't add anything to the null set. It's just nothing. So anything intersected with the null set is going to be the null set. And that's just how that goes. You intersect the universal set with the null set. It's the null set. So in this sense, any subset is dominated by the null set. And that's why we call it a domination law. Okay. So I think this is where things start to get a little more interesting. We've got these absorption laws, and you can kind of see why they are called absorption laws. We have some somewhat more complex statement here on the left, and all of this can be sort of reduced. It kind of absorbs into a single value, as we see here. I think they probably call this absorption because in this case, A is absorbing through the union, the intersection of A, B, or A through intersection is absorbing the union of A or B. So I think that's why they call it absorption, because we've got this value on the left. But this falls into the family of what I would think of as reduction properties. So let's walk through one of these. Let's name A as true and B as false. And so if we think about this, so A union, and we're thinking about union as or, right? So A, well, let's call this true. True or true and false. So we're going to expect this to simplify down to true, right? According to these laws. So let's just walk through it. So true and false, well, not for and, both of those have to be true. So true and false is going to evaluate to false. True or false is going to evaluate to true. So that's nice. We see that works. And let's look at this next one. So true, I'll do this, true or, my apologies, true and, true or false. Again, we're going to expect this to simplify down to true. True or false is true. And then true and true is true. So you might already be thinking about this. We can actually construct very complex logical statements and simplify them via these kinds of laws. And there are some, these can get really hard, actually. They can get very tricky, and often when you're writing code, if you're writing complex logical statements, you don't necessarily need to simplify your logical statement. I'm just going to say that right now. If it's a Boolean operation, right? It's you can use nested ifs, and you can create something very complex that will work just fine, and you're not going to hurt yourself in terms of runtime, not necessarily. But you can imagine you can write much more elegant Boolean expressions that handle and get rid of the need for nested if statements if you simplify your logic. I'm not suggesting you put a significant amount of time into something like that, because at this stage you are really just writing code, right? You're trying to make something that works, and I think that's much more important than optimizing your code at this stage. In the future, of course, you're going to optimize code. You're going to write something, get it to work, and then refactor it to be much more efficient. But that's post-technical interview, and I'd say you're not going to hit stuff like that until you're in maybe the third week of the DSI. So let's consider this identity property. And I think this one's pretty obvious. If you union anything with nothing, right, you're not putting anything into nothing. You are you're going to have the thing that you started with, right? It's like, hey, I've got all this stuff. I'm going to add nothing to it. I still have all this stuff. So I think that one is pretty straightforward. Now, these two, I think they're a bit philosophical, really, but I think they're also fairly obvious. What's the opposite of nothing? Well, everything. What's the opposite of everything? Nothing. Oh, and just as a reminder, these tildes, these just mean not. Okay. And yeah, let me just remind everyone of some symbols, because we're getting into the use of complements here. So, or the essentially not operations. Okay. So we can represent not in a few ways. In Python, obviously, we say not. Sorry, and I'm going to call this not and complement. In Python, we say not. In our set notation or in Boolean algebra, we've got a number, or in formal logic, we've got a number of different ways to represent this. I'm just going to do this with the character A, the set A, or the Boolean container, right? Boolean variable A. If I want to say not A, I can say it like this with a tilde. I can say A over bar. I can say A with a little C up here for A complement. In formal logic, a lot of the time you'll see this sort of like sideways L, or, it's like a little bar for not A. And then a lot of the time, you'll just see people do this. They'll just write not A because, human language is nice. I sort of tend toward this one, this overbar A, and I'm probably going to write a little bit later, I'll probably write this as overbar A. I find this easier to read, and also it comes from circuit design, so I have some background in computer organization. So I think this one's really nice. It doesn't clutter up the space. Unfortunately, when you're in our text-based writing systems with a text processor, we don't really have much ability to have an interpretable overbar A, right? So we will tend to use this not A in text. Or, I'm using tilde in our notes. So hopefully that doesn't get anyone too confused. If you don't know what the symbol is, it probably means not. Is what it comes down to. We just have so many of them. Cool. Let's go from there. This one's pretty obvious, I think, as well. So if A is true, then, not true, not, right, double negative, just leads to, an elimination of the negative, right? So not true is just going to be true. And, if we want to be exhaustive about thinking about this, so true, if I say not true, if we're thinking about this in terms of Python, well, not true is false, right? And then not false just equals true. Okay. Now, there's this amazing law that if you do computer organization or you do circuit design or anything like that, there's this amazing logic law that comes in handy. You end up using it all the time, and none of us know what it's called. Nobody on my team knows what it's called. I've asked other people. If anybody knows what this law is called, that's great. But I'm just going to call it a helpful unnamed law. So let's consider A to be true and B to be false. And let's just construct this, okay? So we've got true. Oops. We've got true and false, or true and not false. And order of operations here are ands, and this is sort of intuitive. The and operations precede the or operations, but just for clarity in everything, I've been parenthesizing them so that we don't get confused about that. So let's do true and false. Well, true and false evaluates to false. And then true and not false. Well, let's just take care of this not false first and turn that into a true. So there's going to be false or true and true. True and true, well, that's just true, right? Then we've got false or true, and we've got a true in there in the or operation, so that just evaluates to true. And we can see that A is true, so that law holds. And with a lot of these laws, you can, if you perform these kinds of operations, you can actually build new laws that hold. This is one nice thing about formal logic. It is consistent. It is like truly consistent. And you can take a productive approach, right, where you start with just a simple Boolean statement like true, and then you say, well, true is equivalent to true and false, or true and not false, right? You can do this if you're really bored. I don't know. I think this kind of stuff is fun, but I also wouldn't necessarily wish it upon anybody, but you do need to know it in the long run. Okay, so this gets us to De Morgan's laws. And De Morgan's laws are really the ones that, if you're going to commit to memory, these are the ones. I mean, there are some other obvious ones, right, in terms of identity and, things that just make sense, like the complement of the null set is the universal set, and the complement of the universal set is the null set. But these are the ones that will get you caught up in a technical interview. So let's walk through these and just justify them, and then I think we will have a little bit of time. We'll just take a couple minutes and think about just a logic circuit, and we won't put too much time into it. But I think it is interesting to see logic in the format of a diagram, in a visual representation. So, okay, let me do that. All right. So I'm going to rewrite these a little bit. Well, first I'm going to say A is true, and I'll stick with this kind of A is true, B is false scenario. And when we're saying A union, we're saying A or, right? A or B. And I think this is what's nice about the overbar. The overbar sits over the entire statement, right? So this is not A or B. I'm just going to fill these in. So this is not true or false. True or false evaluates to true. Okay. And we're dealing with a not true, right? So that just evaluates to false. Now, I could walk this back and make this sort of purely Python looking. So I'll just walk through that again. So not A or B is the same as not true or false. True or false evaluates to true. Not true evaluates to false. So we can see that. Now let's consider the other side of this. We've got not A and, right? We're still on the first law. Not A and not B. So this is not true and not false. So not false evaluates to true. Not true evaluates to false. And obviously, false and true evaluates to false. And we can see that those two are equivalent. And then this last one, this is just, we're still dealing with A is true, B is false. So here we've got not A and B, which is not true and false. Okay, true and false. Well, that's false. Not false is true. Okay, so on this other side, we're starting off with not A or not B. So that's not true or not false. Not true is false, or not false is true, right? So that just reduces to true. False or true is true. Okay. So I know that this is still a bit of a, like you're watching you're watching something that's somewhat abstract, but we can connect this back with Python as I do in these notes, right? We've got a whole structure here that we can, we've got a lot of examples here in both Python and in set operations. Now, I didn't put set versions of these for anything that had a complement because, well, if you're going to take the complement of a set, you need the superset, right? And even though I could do that, the complexity of it is just not important for what we're doing right now. But all of these same laws will hold. Cool. So, oh wow, this is a huge image. Okay. Let's see if I can just snag this image. So there's some cool things in this image, and I think this is a nice thing to maybe set aside somewhere as well, along with this set of notes. We've got all of our operators here. So I'm going to draw a very simple circuit, and maybe I'll do this in relationship with one of our De Morgan's laws, just to give a sense of how we want to think about a circuit. And when I say circuit, we can think about circuit as being synonymous with a structure of control flow. Actually, it's not. It's sort of fundamentally the same thing, except we're dealing with a Python environment and simple true falses. We're not dealing with binary inputs into an actual physical circuit. But at the end of the day, it's kind of the same thing. We're achieving something similar in terms of how we construct truth. So here we've got a truth table. And this is kind of nice. We're going to think about zeros as falses and ones as trues. And we can see that the AND operation, when we say A and B, well, there's only one instance in terms of the binary input that will achieve a true as output, right? And so if I draw an AND gate, and let's do this. Let's do an input A and an input B. Right, we've got two inputs and a single output. Right, this is an AND operation. So, thinking about this, the only way that we can get a true, in terms of output, a true output, is if both A and B have true inputs, right? If A is false or if B is false, then we get a false output. So we can create more complex circuits, right? We can do something like, let's make an AND gate. The AND gate outs into, let's say, an OR gate. And let's say we've got three inputs there, and then we have an OR gate out here. You can see pretty quickly that this can become fairly complex pretty fast. And let's have all of this lead into an OR gate out here. Actually, let's do an AND gate out here. Let's do a NAND gate, which just means that the AND will evaluate, and then we not the result. And we do that with this little circle right here. So here we've got a circuit. And so, and I'll annotate these. So this is AND. This is OR. This is OR. And this is AND. And then the result of the AND, we not. So I'm going to put some input values into this. And, take a minute and evaluate those inputs and tell me what the result of this whole operation will be given the inputs. So I'm going to set this to false and false and true and false and true. So yeah, take a minute, and as soon as you get to a result of this, go ahead and throw it in the Slack, and then we'll work through it. Okay, so I'm seeing a lot of people saying false, and I'm not sure actually. I haven't worked through it yet. So let's just walk through it and see where we get. So false and false. Well, that's false, right? So we can just put a false as our input, as one of the inputs to OR, and then this second input to OR is a true. So false or true. Well, that's true, right? And then, so we've got a true input here to this last and this NAND gate, not AND gate. Okay, and over here we've got false or true, which leads us to a true. So true and true, well, that's true, but then we hit this not right here. And so not true is false. Now, I suspect we could simplify this, but instead of simplifying it, if you want to simplify it, by all means, please. We can take this and translate it into a Boolean expression. Okay, so let's do this bit by bit. So not and, right? So I can say we've got two inputs here. And let me call these, what's a good way to think about this? Let's do this. We've got a bunch of inputs, A, B, C, D, E. And we can say A and B. So A, and this is one of the symbols we can use, this little time symbols, but I'll just say A and B. I'll just put them together like that. Okay. And then the result of that is going to be ORed with C, right? A and B or C. We can wrap that in parentheses. And then that's going to be ANDed with something, okay? That's going to be ANDed with D or E. And the result of all of that is going to be knotted. It's going to have a not bar put over it. And just to be consistent, I'll do this. So not all of that. So you can see here that we've got a Boolean expression. I could translate this directly into Python, right? Just not open parentheses, open parentheses, A and B, close parentheses, or C, close parentheses, and open parentheses, D or E, close parentheses, close parentheses. That is a valid Boolean expression. Offhand, I'm not sure about simplifying this. I think it can be simplified, but it's fairly complex, and I'm not going to take us through that right now. I just invented this on the spot, so. But I'll challenge you to try to draw a circuit. I don't mean right now in class, but outside of class, try to draw a circuit and translate it into a Boolean expression, and then try to in like a Pythonic Boolean expression, and then then define a Boolean expression and translate that into a circuit. Oh, my dog's barking. Okay, so let's stop there in terms of axioms of probability. And when we come back, we're going to build another lens on probability through, we're going to continue an idea of sets in terms of probability, but we're going to approach this with counting and approach probability through counting. And we're going to use counting as a basis for understanding probability from here on. As the primary basis for understanding probability from here on. So let's take 6 minutes, and I will try to calm my dog down. Okay, I'll see y'all back here in a few minutes. Okay, let's start thinking about probability. And we're going to kind of build the basis for probability a little bit out of set theory, just to see that we're working with the same materials at the end of the day. Okay, so there really should be other bullet points here. I was building this deck just before class. Okay, so we're going to think about this concept of cardinality. Now, cardinality, I think of maybe in terms of magnitude, and really it's just how many elements are in a set. So we represent this fairly simply. We can just use these vertical bars, sort of like like magnitude, and we can see that in this first set S, our superset S, we've got 8 elements, and so the cardinality of it is 8. And A has 4 elements; the cardinality of that is 4, right? In this case, the actual elements are these numbers, right? 1, 2, 3. These are all elements of S, and we can see that A is a true subset, is a subset of S, right? A does not contain anything that is not in S, and and A contains elements that are in S. So A is a subset of S. Now, we can take this a little bit further to express probability. We can express probability as being a ratio of cardinality. And all I mean by that is that if we are trying to ask the question, what is the probability of achieving event A? Well, what comprises event A? Well, it's either we get a 1 or a 2 or a 3 or a 4, right? If we're randomly sampling out of our entire sample space, what is the probability of getting event A, which is, 4 of the elements that exist in our sample space? Well, we can just take the cardinality of A and divide it by the cardinality of S. And essentially what we're asking here is, well, if we've got the numbers 1 through 8, what is the probability if we weight these evenly, right? If there's a 1/8 chance of any one of those, what is the probability of getting 1, 2, 3, or 4? Well, it's kind of obvious. That's 4 out of 8, and it's 0.5, right? So that's a way to think about probability as being expressed through, drawing things out of sets. So let's think about this a little more, right? What is the probability of rolling a fair 6-sided die and the result of the roll showing an even number of pips? Pips just means dots. So if we think about this, that's either a 2 or a 4 or a 6, right? We either get a 2 or a 4 or a 6. And, well, that's 3 elements. So our subspace, which we're calling A here, we're defining as an even number of pips. That set is composed of 3 elements. Cardinality of it is 3. So we can just divide 3 by the cardinality of S, which is 6, right? Because there's 6 sides. And we can see that that's just 3 over 6 or 0.5. Okay, so this is, in general, this is the notation we're going to be using. And I want to kind of just expand on this a little bit. I'll put this here. If we're thinking about probability, I'll expand on this. So this is a very common notation where we say the probability of something in these parentheses. Now, a lot of people will actually write out prob or probability of the thing. And that's just, dependent on their background. I really prefer this. It's just quick and easy. And what we put in the parentheses can be fairly detailed. Okay, so we can say probability of rolling even on a single six-sided die roll, right? We can detail it that much, right? And I think just being expressive enough is important, but it can be cumbersome if you're writing a lot. So often what we will do, I don't do this as much, but often what people will do is define an event A and say A is the event of an even roll of a six-sided die, and then we're asking what is the probability of, say, not A. Okay? And that way they're not saying the probability of not rolling an even roll like in this big long text inside of here. I like naming things meaningfully when I do this because I get confused if I'm constantly referencing back to a table. So, the probability of drawing a red ball, let's say, I might say probability of red or R instead of defining A as drawing a red ball, I would probably just say probability of red. And that's really your call. It's up to you how you want to represent those things. So there's a few things in here to notice. We're thinking when we say something like probability of A union B, we can think about this as the probability of event A occurring or the probability of event B occurring, right? And that, just we're still continuing with that analog in terms of logic and sets. It'll be a little bit different how we might think about the intersection of A and B, because, and we'll see that when we get to dependence. When we get to Bayes' theorem, essentially, when we get to Bayes' theorem. But we won't worry about that too much right now. We're going to shift over to a perspective in counting. Now, I just want to point this out for, before we move forward. This bar here, this is the probability of the event A occurring given that the event B has occurred. And this is a huge part of probability theory. We're going to devote a whole lecture to this idea, and so I'm not going to get too much into it right now. But I just want to point out that that's how you would read this: the probability of A occurring given the probability that B has occurred, or the probability that B will occur. It's actually independent of time. Okay. So, this is something not very many people teach probability through the lens of counting. And I do this because we're thinking about things very procedurally as people who are programming a lot. We want to be able to define a procedure that helps us get to an answer. And if we have a rudimentary brute force approach that we can always use, then we can always make something happen. It's right. It's like, okay, let's say you want to dig a gorge as deep as the Grand Canyon. Now, there are probably really good tools to use, really complex, sophisticated tools that you could use to do that. Or you could grab a shovel and a bunch of your friends and work at it for a really long time, right? You're still going to get there. And counting is sort of like that shovel. So we're going to approach this, we're going to approach probability through the idea of the shovel, because the shovel is sort of like this universal tool, right? Or a hammer is kind of a universal tool. You could get thousands of your friends and dig the Grand Canyon with a bunch of hammers. Wouldn't be great, but you could do it. And so we want to think about counting in kind of a in a somewhat abstract way, or maybe in a new way, maybe in a way that isn't rooted in our current numbering system. So let's think of a number system that is composed of a cat, a dog, a ferret, and a goldfish. Okay, so we've got, and I'm just going to use the letters for these. So cat, dog, ferret, goldfish. If we're going to count in this number system, the first thing to notice is that we've got 4 elements in here, 4 unique elements. So if we're going to count in this system, we're going to start at something that's arbitrarily defined as quote-unquote 0. So maybe cat is 0, dog is 1, ferret is 2, and goldfish is 3. Now we could translate this into we could just say, well, this is a base 4 system because there's 4 elements, and we could count this numerically. We could say 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, and then when we get to 3, we roll this back over to 1, and we also modify this next value and roll it over. Oh, sorry, we roll 3 over to 0. My apologies. And then we modify the 0 and roll it to 1, right? And the next value is going to be 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 2, and so on. Now, instead of abstracting this to numbers, we can simply just do this. We know that our initial element that we are, let's say, assigning to the first value, which is 0, we can just say C, 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 D, C, 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 F, C, 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 G, C, C, and then we roll the C over, right, to D, and we roll the G over back to C. So C, C, D, C, and then we can keep going, right? C, C, D, D, C, C, D, F, C, C, D, G, and so on. And we can be exhaustive here, right? This is a way for us to be exhaustive and get every possible outcome. Now, if we think about this in terms of, I'm going to randomly select 4 pets, and when I select those pets, I reach I don't know, maybe they're all in a room, and there's an equal chance of me reaching into this room and pulling one of them out. So I pull one out, and I look at it, and I write down what that is, and then I put it back in the room. And then there's equal probability for the next animal, and I pull that out, and then I put it back, right? So I do that 4 times. How many different ways how many different outcomes are there? That's really the question, right? How many different outcomes? Now, we can be exhaustive and we can count them like this, and we're counting from C, 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 C all the way up to G, 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 right? Pull out the goldfish 4 times. Now, we can do this exhaustively, but is there an easier way to just determine how many outcomes there are? Does anybody have a thought on that? Just throw it in the Slack. If you think you know how many outcomes there are, just put it in the Slack. Now, it may not be obvious. So factorial 4, this is the thing. Your factorial 4 would be correct if we were talking about permutations. We haven't gotten to permutations yet. We're doing pure counting. Permutations is a type of counting. 4 cubed Does that sound right? 4 to the 4th power. Yeah, 4 to the 4th power. And this is going to come back around kind of a lot, actually, because I like teaching out of this paradigm, because I think it gives a very solid foundation in what it means to construct the set of outcomes and a subset of the outcomes. We can use this brute force approach and use some control flow and determine a probability. So 4 to the 4th power, we can start thinking about this in terms of selecting one pet, right? We select one pet. Well, that's either going to be a cat, a dog, a ferret, or a goldfish, right? And then if we're going to expand on this and select two pets, that's cat, cat, dog, cat, ferret, cat, goldfish. And I'm not going to go through all of these, but we can see that we can count this by hand. We can write out all of these, and if we were to count them up, this would be 4 squared. So DC, DD, DF, DG, right? And this wouldn't take too long, but you can see where we're going, right? And we get down to GG. That is going to be 4 squared. That's going to be 16. Okay, so how do we do this in Python? I put some code for this here, and I'm going to walk us through this code, and then I'll code a different example, I think. So here we've got our pets, cat, dog, ferret, goldfish, and we're going to construct all the outcomes, just pet outcomes. I'm making an accumulator here for pet outcomes, and then pet 1, pet 2, pet 3, pet 4. I am going to loop through this, and then I'm going to append every one of these. So the first time this happens, I go into this initial part of the loop, and it's cat. Then I see here, pet 2, I go into the inner loop. That's going to be cat again, and then cat again. And then so the first element, the first outcome that I append is going to be cat, 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 cat. And then I'm going to stay in this inner loop for its second iteration. So this second loop is going to be for dog in pets. And so pet 1 is going to be the same, pet 2 is going to be the same, pet 3. These 3 are going to be cat still, and pet 4 is going to be dog. And you can see that we're going to be counting by doing this. We're going to be counting through this system by doing this. And we get some output that looks like this: cat, 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 dog, cat, 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 ferret, cat, 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 goldfish. And then notice we roll dog over right there. Huh, that's funny. All right. So I'm going to put this this snippet of code into the document that we're going to be using. And I think the next thing I have here is a challenge. Yes. Okay. So you're going to need this slide, and why don't I just drop this code into the Slack as well. You're going to utilize this code to solve this challenge. So what is the probability that a person will select 2 or more cats when randomly choosing 4 pets with replacement? And all I mean by with replacement is that you reach in, you pull out a pet, and then you put it back in the room, right? So you're going to be doing that every time. So you can pull the cat 4 times, or you can pull the dog 4 times, or 3 times, or anything like that. So what is the probability that a person will select 2 or more cats, or select the cat 2 or more times when randomly choosing 4 pets? So you should have everything you need to solve that. And yeah, I'm just gonna put 4 minutes on the timer. And when you put your answer in, you can put if you are solving this with code, and I suggest you do solve this with code. I put in your code snippet as well. So put in the code snippet and put in the result that you achieved. All right. So, if you were stumped by this, don't even worry. It's uh, the thing about this kind of problem is that we're going to do this sort of thing a lot, and we're going to take this exhaustive approach, and we're going to get to we're going to use this brute force approach, and we're going to sort of skirt around the math until we start using the math, right? And we're just gonna get a lot of practice with this. So I'm gonna go ahead and code through this. So what was the question? 2 or more cats, I think, is what we were talking about. So we've got our pet outcomes. we can just traverse the pet outcomes, right? So for pet outcome, in fact, I'll just copy this, and instead of printing it, I will start collecting into a list that I'm going to define as 2 or more. I'll call this 2 plus cats. And the only reason I'm collecting into this, we could use a counter. I noticed everybody used a counter who provided code. That's fine. In this case, I'm just sort of exemplifying here's a subset of S that's called 2 plus cats, and then we'll take the cardinality of that at the end, just to follow with the pattern that we've been talking about. So if the pet outcome dot count of, and I think I just named it cat, of cat, if this is greater than or equal to 2, then we can say 2 plus cats dot append. We can append that particular outcome. So we can append that outcome. What I'm going to do here is also traverse the 2 plus cats list and call this cats in there. Let's print the cats just to get a sense of this, because I think this sort of reduction will maintain a kind of pattern consistency, and we'll see that. We'll definitely see that when we get to permutations. We'll actually utilize that when we get to permutations and combinations. Okay, so the outcome of this is just going to be the cardinality of 2 plus cats, right? So the cardinality of the length of 2 plus cats divided by the length of pet outcomes. Yeah, okay. So let's see if that works. Yeah, that worked. And that looks like the same outcome that everybody else is getting, 0.2617. And we can see here, right, cat, 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 dog, cat, 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 ferret, goldfish. And then we start shifting these other values in. And we're not going to talk too much about shifting. Well, maybe we will. I might build out part of our counting lecture to include a shifting approach that is different from a counting approach, but I'm getting ahead of myself, so I won't say too much about that yet. Okay. All right. Oh, that looks almost word for word. It is word for word. Okay. All right. So the next thing that we're going to do, this is going to seem like we're stepping a bit off to the side, but I want to kind of bring in another concept here, because what we are really talking about is a random or stochastic process of some sort, right? We just built an exhaustive way to see the outcomes of some random process. All potential outcomes of a random process. Well, where's the randomness? We want to think about this also in terms of an actual random process, right? So the next thing I'm going to have you write is going to diverge just for a moment, and then we're going to come back. We're going to diverge a little bit from this exhaustive counting, and then we're going to come back and see two lenses on the same thing. Okay, so you're going to write a function called series of flips, and it's going to have, the function is going to have one parameter n that represents the number of coin flips, and you're going to return a list of length n containing n random coin flips. So this is going to be the starter code. So I'm giving you the random coin flip function, and you're going to use this to generate a list of length n random coin flips. So let me throw that in the Slack. And yeah, I'll leave this up like this. So you've got your starter code in the Slack, and yeah, I'll just put 4 minutes on the timer. I think you have everything you need. If you have any questions, just ask in the Slack really quick. Awesome. A lot of you got to a solution on that, and that's great. So I'll just code through a solution here. In fact, let me paste in so that these notes don't get too muddled. snag all of this. Oh, and I'll need that code as well. Okay. And do that. Okay. So we're calling this series of flips. So def series of flips of n. And I'm just going to do a simple accumulator here. There's, you know, slightly, you could write a comprehension here. We haven't covered comprehensions, but if you're familiar with comprehensions, this is a perfect place to use one. So flips gets this and just empty list. And then for whatever in range n, I will just append flips a coin flip. And we can return flips. The equivalent of this in a comprehension would just be to return a coin flip for whatever in range n. So that would be a one-line solution that would do the same exact thing. Okay, so I'm going to test this, and let's see what happens. And let's return 4 flips of a coin. Heads, tails, heads, heads. Tails, heads, tails, tails. Heads, tails, heads, tails. Right? We could do this all day, and we're gonna keep getting random results. Okay. So let's oh, yep, that is the solution. Okay, so the next breakout, you're going to write a function called forFlipSampleSpace. And that function is going to take no arguments, right? So, you know, just def forFlipSampleSpace. And you should return a list of all possible outcomes for 4 coin flips. Offhand, you might know how many that should be, right? But it's okay if you don't. And if you could also include code to print out the results, right? So iterate through and print out the results in a for loop. So write the function and then call the function in a for loop. Call the function and print out those outcomes in a for loop. And here I will do that. I see only one solution in there. Give me a thumbs up in the Slack if you'd like 2 more minutes on this. Okay, I'm gonna put 2 more minutes. Okay, I'm gonna start working on a solution here, and feel free to continue working on your code, and you can reference back. Okay, so we're writing a function called forFlipSampleSpace, and let me put that in there. Okay, so I'll just define this really quick. forFlipSampleSpace. It takes no arguments, so I'm not defining a parameter. I'm just going to say, right, we've got 2 potential flips. We've got heads and we've got tails. It doesn't matter what order I put these in, tails or heads is fine either way. So we've got our outcomes, and then there's flip 1 in flip, and then 2, 3, 4. Because this is sort of this pure counting, we can just nest loops to do it. Now, there's a certain point where this becomes intractable, right? Like, okay, you flip the coin 3,000 times, right? That's not, we can't actually approach solving this effectively in that way, unfortunately. But depending on time constraints today, I'm going to show you a way to approach solving that type of problem. Okay, so outcomes.append, and we can append F1, actually needs to be in a list, F1, F2, F3, and F4. And then we can just return the outcomes. And I'll just get that, I'll just put that into its own list, because we're going to need that. And I'll say for outcome, in outcomes, let's just print the outcome. Okay, so here we have our sample space. And if you count these, you're going to see 16. And if you think about that, that's 2 to the 4th power. 2 times 2 times 2 times 2. So we can see that base, the cardinality of the space, in the way that we're approaching these, the cardinality of these spaces when we're counting is going to be the number of elements in the set to the number of positions of the quote-unquote number that we're creating. It turns out that what we did here is effectively the same as binary. There isn't really a difference here. We could say that heads is 0 and tails is 1, or heads is 1 and tails is 0. We're going to be talking a lot more about binary pretty soon, because it turns out it's a very helpful basis for understanding some of the core probability concepts, especially distributions, the binomial distribution in particular. So let's see. All right. I'm going to solve this next one. I think I made a challenge for this. Yeah. There's that. Okay, so what is the probability that in 4 coin flips you get exactly 3 heads? And here's the basis for it. This is not unlike what we did before with 3 or more cats. And for that reason, I'm just going to solve it really quick. So probability that in 4 coin flips you get exactly 3 heads. Well, we can just traverse through our outcomes. So for each outcome in outcomes, let's call this 3 heads. And for each outcome in outcomes, if outcome dot count of h is equal to 3, and we're talking exactly 3 heads, so not greater than or greater than or equal to. And here 3 heads. I'm just going to append the outcome, and let's print the 3 heads and just see what those look like. And let's also print the probability. So this is just going to be the length of 3 heads divided by the length of the outcomes. Oh, what did I do? For outcome and outcomes, if outcomes.count of heads is 3, 3 heads dot append outcome. Anybody seeing my error here? The S. Ah, thank you. There it is. Wow. That's much better. Okay, so when we're thinking about the actual outcomes that meet this condition, and I just want to seed this idea, we can count through all of the outcomes to try to figure out how many have 3 heads in them, or we can figure out a way to count, a way to just shift the tails across, right? Because it's the difference between performing 16 operations and performing 4 operations. That's just a seed and idea. I'm not sure if we'll explore that that deeply. There's an opportunity to do that when we're talking about permutations and combinations, because we're going to take this kind of brute force counting approach when we approach this brute force counting approach when we work with permutations and combinations, and it's not going to be the most efficient way. But if I can make it work where I teach a more efficient way, where we have this counting approach, and then next to it we show a shifting approach, I'll do that. But I also don't want to, inundate or be too confusing about some of these things. At the end of the day, the main thing that we want you to be able to do is have an exhaustive, brute force counting approach that uses an accumulator pattern to solve almost any kind of problem that comes in front of you, and which this approach really does. If you have enough computational power, that is, and as long as the problem is not intractable. So I wanted to bring this back around. So what was that? That was 0.25. I want to bring this back around to the function above where we have this random process. Okay, so with this random process, we can also solve that prior question. We can approximate a solution using a random process. Now, this is all in good, right? This counting approach is all in good when we've got 4 coin flips. But again, what if we had 3,000 coin flips? So maybe I think as long as I don't have too many egregious bugs in here, I think we could do this. So let's ask this question: how would you find the probability of getting, how about 1,800 heads in 3,000 coin flips? How about not find, but estimate? Because that's what we're going to be doing. We're going to be doing an estimation. And I'm just going to say this offhand. Do not use the binomial theorem, PMF. Okay. I know you don't know what a PMF is yet. A lot of you don't know what a PMF is yet. We're going to be working with those soon. Not in the next class, but in a couple classes. So there is a way, and maybe I'll just allude to this. We could ask the question, if we know the probability of heads, we could use a pre-built formula called the binomial PMF and say, well, there's 3,000 coin flips, and we're wondering about the probability of 1,800 heads in 3,000 coin flips. The probability of getting heads is 0.5. If we have those 3 things, there is actually a closed formula that will give us an exact probability. Now, if we don't, that's a fairly simple probabilistic process. A coin flip is fairly simple. If we have something more complex, we're not necessarily going to have a closed formula for solving it. And I want to kind of, give a sense of another way to solve this using this this coin flips. What is it? This series of flips function that we defined earlier. Okay, so series of flips of 3,000. Now, how about I don't print the actual series of flips, but I print the count of heads in 3,000 flips. So let's take a look at that. 1,448, 1,487, 1,531. Okay, so if I want to determine an estimated probability, a way that I can go about this is I could say, well, let's have a number of trials. How about a number of samples. I'll call it samples. And let's just do 100. And what I can do here is say, for whatever in range num samples, let's append to a list. We'll call this heads counts. Let's append to a list called heads counts the counts of heads, right? And so let's, and then we can, at that point, we can print the sum, and this is going just back to the average, right? The sum of heads counts. divided by the number of samples. So on average, notice that what we're getting here is the average number of times we flip heads, right? So that's kind of cool. Now, how about how would we go about answering this question? The probability of getting 1,800 heads in 3,000 coin flips. How would I modify this code? Yeah, I mean, here's the thing. We're not taking enough samples in this case to be able to answer this with this approach. We would have to take quite a few more samples. And what I would likely do is append a true-false statement here. And that's what I'm going to get here. How often is the count of heads? 1,800. And so now we can sum the, we'll call this heads 1,800. Divided by the number of samples, and then we get 0. If I run this again, 0, 0, 0. At some point, we are going to get 1,800 heads, but let's see if we can increase the number of samples and get there. Now, every time I increase this number of samples, it's going to take longer and longer to run, right? And we at some point we need to decide, is this problem intractable? Right? At some point we have to decide whether or not we have the computational power to really solve this within a reasonable amount of time. And in this case we don't. In this case we would want to use the binomial PMF. And even then we're going to lose a lot of precision, and we're going to get something pretty much 0 when we get down to it. So let's change this a little bit. Let's think, how would you estimate the probability of getting 18 heads in 30 coin flips? And we're going to see that this isn't so bad. So let's do 30 and count 18. And I know we just hit time. If you want to just stick with me 2 more minutes, and we'll see a result here. Okay. So I'm taking 10,000 samples. Let's try 100 first and make sure that this is working. Okay, 0.15, 0.13, 0.07, 0.07, 0.08, 0.08. As we increase the number of samples, we're going to gain surety. We're gonna lose some uncertainty around our probability that we're seeing. 0.077, 0.0822. This seems to be floating right around 0.08. And we could verify this exhaustively, right? We could do this count of 30 flips, but that's 2 to the 30th power possibilities. And we're going to have to think of all the different ways that 18 heads can sit across 30 flips. So this is a good candidate for this sampling approach. It's also a really good candidate for the binomial PMF, which is just that closed form formula that'll give us an answer. Okay, let's call it there. That's kind of a lead-in into future lectures, because we're going to be doing sampling when we get to counting. when we get to permutations and combinations, and we're going to be doing sampling all the way through discrete distributions. So, yeah. Thanks so much. Stick on if you have any questions, and I'll stay on for 10-15 minutes and be available for then. And yeah, have a great rest of your weekend, and I'll see you all on Monday.